would like to complete the course by first explaining what I call Cartan's and let me emphasize, this is the father Cartan, Cartan. And the son Cartan is also not very important in many areas of mathematics. So the son is called Henri Cartan, the father is called Cartan. His dichotomy and his first class is the two classes. The curvature is invariant. So let me make sure you know what I mean by curvature being invariant. It means, i.e. By parallel transport. But let me formulate that in another way that maybe you like better. It means that the covariant differential of curvature is zero, curvature is parallel, for every vector field X. So this means invariance by parallel transport. And another thing, curvature is not invariant. That's the other class. Okay. And then, in this class, there is a great deal of modern work. So let me tell you what happens first in class 2. And then the rest of my lecture today will be about class 1. Okay? So there is modern work. For example, of Berger. Much work in the French school, and some corrections and adjustments by a number of people. The one I know best is, I mentioned this morning, by a very nice mathematician at Duke University in Bremen. So here is 2a. So I have to say something here. The assumption for all of this, the assumption for the classification is irreducible holonomial representation. Let me remind you what that is. I've talked about this before, but there's a lot of stuff going on, and I know you've forgotten it, so let me speak about this before, again. Remember, the holonomial group acts of this connection acts on the tangent space just linearly. It's a group of linear transformation. And irreducible means, when I want to say irreducible, means no invariant subspace. And by the way, I know there's still two physicists in here who thank you very much for staying for all of these lectures. But I'm going to assume in this discussion all the time today that this is really a Riemannian manifold. I am not allowing negative mixed signature metrics. Okay? So for relativity theory, if you want the same result for relativity theory, ask me about it, and I will be able to give you what version you need if there is a result. But it's another theory in that sense. So I'm going to assume here that Mg is Riemann. It's not completely necessary, but it makes my life a lot easier for this lecture. So we have a Riemannian manifold. We have a connection. And I talked this morning about when we have this connection, it just means that you take a connection and you have to check that the holonomic group lies in a compact group, and then you have the invariant metric and everything's okay. So we understand that perfectly. So we have with this connection here, we have, and you ask whether the curvature is invariant or not by parallel transport. That's one class of Cartan. And another class is the opposite, where it's not invariant. That's whatever. Okay. And there's modern work of various people. I think the thing to read if you're interested is the most recent paper of Bryant, who, but the Berger class modern work. And there are two types of results in this modern work. Oh, everything under the assumption that the holonomial is irreducible. And here we have the Durand theorem. This is not hard to prove, the Durand theorem. I outlined it for you what it is. Is this, you decompose, so if M is simply connected, my notation for simply connected means it's equal to its universal cover. So we assume it's simply connected. And we decompose the tangent space, which we can always do, with respect to holonomy, into irreducible representations of the holonomy. So let me write this V1 through V, I don't know, some M. So this requires a little thought, but not much. If you have this representation of this holonomy is compact because it's a Riemannian metric. So if it stabilizes the subspace, it stabilizes the orthogonal complement. So then you have a direct sum between the subspace and orthogonal complement. Then you might have some more and more and more and more and more. So you break this up until you're finished. Okay? So this is the irreducible decomposition. You can break this up. And the incredible theorem, and it's not hard to prove, is that then this gives you a product structure on the manifold. A corresponding product structure. I find this very surprising, but it is this miracle of holonomy. It's the miracle of parallel transport. So you see, if you have a splitting of the tangent space here, that's the splitting of the original tangent space, say into V1 and V2, right? Then this is holonomy invariant, V1. This is holonomy invariant V2. So I move this thing over here with holonomy, with a curve, with parallel transport, right? This is parallel transport to some other point of V1 and parallel transport of V2. So I move all over the manifold. I go outside, and as I just do, I go to the toilet and have some fun and so on. Yeah, it's fine. But I'm moving these tangent spaces all over the manifold with parallel transport. Right? So you're coming close to given a decomposition here. I've decomposed the whole vector bundle. Okay? Just because you have a decomposition of the vector bundle does not mean that that gives you a decomposition of the manifold. Okay? However, in this case it does, and that's the Ram's theorem. Okay? So again, you use holonomy to reduce the situation to manifolds M1 through Mn, where holonomy is irreducible. You can't reduce anymore. That's extremely useful. So we assume holonomy is irreducible. And that's that. And then there are two cases. And case one is holonomy group acts transitively on the unit sphere. In the tangent space.
So each of these subspaces is...
This might
okay. So each of these subspaces V1 through Vm are irreducible, right?
That's right.
Are invariant under the
holonomy.
action of the holonomy.
That's right.
Group. How does that again lead to...
Let me just say it again. I drew it with a picture, and let me say it again. Okay. Then with parallel transport, I can transport V1. I take a curve. I transport V1 to some other point. I get some subspace, and I transport V2 along the same curve to another point. I get another subspace.
So if it's
now you ask, and of course you've got this question in your head: is that well defined? Because it depends on the curve, right? But if I take two curves, this gives me a closed curve that gives me an element of the holonomy. But that holonomy respected the original decomposition V1 plus V2, and so that means this transport argument is well defined. That gives me a transport of the original vector spaces all over the manifold. That gives me a decomposition of the vector bundle into a direct sum of some subbundles. That's almost trivial, as you see. But what is not trivial is that's what we call involutive. It says that these really correspond to submanifolds because it's parallel transport. Okay. But that was Durham's theorem. It's a very good theorem to have. It means you can reduce this thing to irreducible holonomy representation. That's really good. So this is Durham's theorem. Ram, a Swiss mathematician at that time, well, he's not living anymore, but a very, very wonderful person, and did a great deal of help. I think I mentioned this. Very kind person for many people in mathematics in Lausanne. So either it acts on sphere or it is special holonomy. And this is the Berger classification. Berger et al. So this is a very precise classification of what it can be. Okay, and as I say, Berger forgot some cases, and then these cases were rediscovered, and there's some exceptional cases of Lie groups. So the holonomy is some Lie group, and you might as well say it's connected. The disconnected part is not important. So I mentioned it in previous lectures. So for example, Kähler, for example, the Kähler case, which we like in complex geometry, Kähler is really the holonomy is then a unitary group. And so G2 appears here. G2 is an unusual Lie group. Lie groups are combinatorially classified by things called Degen diagram. And the Degen diagram here looks like that. That's a little bit, you may see these Degen diagram pictures. It means something, it doesn't matter what it means. But it's an exceptional thing. It's not in a series like UN, SON, SLN, right? SPN. So this is, and in physics, this G2 holonomial started to play in the last year. It's important. Okay, so that in some sense, you have two cases. In the generic case, it acts transferring on the unit sphere. That's good to know. And you have this other case where curvature is invariant. And I refer this to the Cartan dichotomy. One of two things happen. And then there's the theorem of Durand, of Cartan. It's, to me, an amazing theorem. I'm going to state it. Cartan's theorem for the simply connected case. It's easier to state this way, but it's equivalent. So for M, simply connected. Otherwise, what you do is you just go to the universal cover. You just go to the universal cover and apply Cartan to the universal cover. This is not a hard, so a reference for this theorem, I would suggest C. Helgeson. Maybe it's chapter 4. Well, I know, chapter on affine symmetric spaces. Here's the theory. Here's the theory. Curvature is invariant as above. If and only if so again, I'm assuming it's simply connected. Otherwise, it's only a local statement. If and only if M is a symmetric space. Now, since I have not talked about the definition of symmetric space, you cannot be excited about this theory. But I wanted to write the theorem on the board for reference. So this is curvature. I mean, at least you must. Curvature is something that has nothing to do a priori with symmetry. So curvature is invariant. You know, it has where do you see symmetry? Maybe you see some parallel transport. It all stays the same. Maybe you see some symmetry there, right? So, but yeah, okay. Curvature is invariant by parallel transport if and only if you have a hugely symmetric object. Okay, and so the examples, I'll write them on the board again. I wrote them maybe yesterday or this morning, I can't remember. Example of all in dimension of M equals 2, then M is either equal to the disk, the plane, or the sphere. not bad, right? In dimension 2, your favorite manifolds, there are only 3 such manifolds, and every 2-dimensional manifold has such a structure. So in some, you prove every 2-dimensional manifold has such a constant curvature structure, and then therefore in dimension 2, the manifold classification is the disk, the plane, and the sphere. Simply connected. So we have to mod it in general, we have to mod out by the fundamental group action. Right? Okay. And you see in dimension 3, even in dimension 3, there is a big Lie group role played in Thurston's classification. So, yeah, it's well, a very amazing mathematics. So, what is the symmetric space? Well, let's take M. And let me emphasize the word globally. You take M, and you take a point at M, and you know from the very elementary theory of differential geometry, basically of Gauss, you have the exponential map from some neighborhood, some nice neighborhood contained in the tangent space at this point, so a nice open neighborhood, maybe coordinate neighborhood in the tangent space here at this point, into M. We have the exponential map. You remember what it is, I hope, right? It means that if we take a line. Here's the tangent space, and here's a line in this tangent space, x0. And if you have a point here, this is the element c in that line, and so you write x c. So we maybe take xc, we take a particular point c0, and then the rest of these things are just times t. C0 times t, a positive line. Usually we go geodesics in the positive direction, but let's take the full thing, positive a line, and you go x of c0t. Right? That's the geodesic. That's the geodesic defined by c0. Right? That's what the definition. I did it this morning for multiplicative real numbers. That's e to the t. Well, maybe you take, if it's just e to the t, maybe you take something of length 1 here. Who knows, right? Okay, but you're taking some open neighborhood where this is a good mapping, because as you know with the sphere, I was just in an airplane and I know this. It's wonderful to go in an airplane and watch the geodesics on the monitor, right? So in a sphere, you start at the top. You have the exponential mapping. Here's the tangent space, and then you have the exponential mapping. These are the geodesics on the sphere in the airplane, and of course we don't fly that far at once. But of course they come. You have the problem that they all come. If you start at the North Pole, they all come together at the South Pole. Right. So you don't want that to happen. So you only take a small neighborhood, so the small neighborhood of the tangent space here comes down to a beautiful neighborhood here. Which is a diffeomorphism. So this is a diffeomorphism, right? The exponential mapping, and so the image of it looks like this. So maybe I'll make a little curve to remind you that these are really geodesics on the manifold. This is the image of the exponential mapping. This is x of u. So each line comes down to a geodesic. Right? This here is called normal coordinates. I'm reviewing all these things for you. Right? This is called the normal coordinates. These are the geodesics. This is a piece of a geodesic. This is a piece of a geodesic. And now, this is the amazing thing that Cartan, of course you can see it if you look at the curvature tensor and all of this. It's not very hard to understand if you're thinking correctly. You have geodesic, you have what physicists call, by the way, I have several papers with physicists in quantum theory where you always have, with Schrödinger operators and so on, you always have something called time reversal. You always have something called time reversal. I have a big difficulty with my physics friends explaining anything in vector bundles or something like this. Yeah. But they understand time reversal as time reversal. So that means if you go out along a geodesic at time t, so this is x of say some I don't know ct. Time reversal reverses it and goes down by minus t, x of c0 minus t. It's a geodesic reflection. You get it? You reflect, I mean, there's no canonical direction in this line, right? There's no difference between positive and negative time. There is absolutely no difference. And so you should say the natural symmetry in this situation reflects positive time, which you don't know what it means. You have this reflection in this situation, time reversal. Okay? So time reversal there, and time reversal here. Maybe let's draw another color. So time reversal here. Time reversal here moves it over here. Right? Okay. Now, believe it or not, you believe it. The sphere is beautifully round, and so you take time reversal here, and you go to here, and here, to here, and so on. But suppose you take the sphere, and take your fist and smash it in on one side, right? And with some horribly, make it smooth, but some complicated curvature on one side. And you have these geodesics going out like this, and you take time reversal. That is certainly not an isometry, right? Because curvature over here will be very, about a negative curvature, positive curvature, or I flatten it out on this side or something like this. You see what I'm saying? There's no reason that time reversal is an isometry. Right? There's no reason for that in general. You just have these geodesic coordinates, and you as some child, and 6-year-old Frederick, can say, oh, I make time reversal, it's great, it's fun. It's great, it's fun, but it's certainly not an isometry in general. Yeah. But curvature is invariant by assumption. So that means everywhere curvature is invariant by parallel transport. So there is some really hope that time reversal is an isometry. Okay? So, globally symmetric means time reversal is defined by a global isometry, and I think I'm going to call this sigma. Of course, it depends on the base point, in the isometry group of the manifold. If you're doing physics and you have the manifold, it usually is very often the case that your time reversal really is acting everywhere. It's a global isometry. By the way, it's really true. And if you really want to use this and impress your physics friends, understand it, and you will prove a theorem for the physicists, I'm sure. I've proved several theorems for physicists using this fact. Okay? It's a global isometry. Time reversal is a global isometry. Okay? Okay. That is the definition of globally symmetric. Locally symmetric means just in the local picture, time reversal is an isometry, a local isometry. But time reversal and local isometry everywhere. You go to the universal cover, and then on the universal cover, it's a global isometry. So if you're willing to pay the price of going to the universal cover, you lose nothing. So we have here simply connected manifolds. So these things are globally symmetric if they are symmetric. Okay. Now watch. Okay, here is I want to transform this point x0. Here's x0, and I want to transform it to x1 by a global isometry. Okay? Well, it's not very hard. Here's how to do it. So I put x0. So I take x0. It's not equal to this base. No, I mean let me call this x0 is a base. Let's say x0 is the base point. X0 is the base point. That's fixed by time reversal. That's no good. So what I want to do is this is fixed by time reversal. So is fixed. I want to move x0 to x1, but I can't by this time reversal because it's fixed. I mean, I can flip this point to here, and I can flip and so on, and then I can flip this point to here and so on. By time reversal, it doesn't do any good. But what do? You see what I do, of course. You know. You're not stupid. So we have x0, and I have this normal coordinates here, right? So then here's x0, and I wanted to map x0 to x1, say, here. And so what I do is I take another x0 here, along this geodesic, x0 hat, along that geodesic, and now I will mess up my picture, but it'll make you understand. Yeah, I take and now I have normal coordinates here. I take x0 hat, I have normal coordinates here, right? And now I can move x0 around x0 hat by geodesic symmetry. Here's say sigma 1 of x0 by this geodesic symmetry for this new normal coordinates. And now I take new normal coordinates here, and so with another point here, and then I move this here to here. Do you see it? So by a sequence of involutions, right, and choosing the right normal coordinates, I can move any one point to any other point locally. Okay? So locally, the isometry group acts transitively. Colin looks mystified by this. Are you really mystified? I'm not sure.
No, it's not.
I think it's okay. It's okay, but you have to choose the right base point for the reflection, and so you have enough of these reflections you can go everywhere, right? So I think that's a completely clear argument, right? So it says the isometry group. So this implies. Let me write what it implies. So the proposition is the elementary proposition. So M globally symmetric implies that now call this G, which is the isometry group of M, acts transitively on M. Now, I would like to, I have to tuck in my shirt here. I would like to talk about that a little bit. So above in this argument where I asked Colin if it's okay, if he buys this argument, so above, above argument, so proof. Above argument, that shows that every G orbit, whatever this thing is open. Right. I take a point. Right. And locally, when I was talking with Colin whether he believed in my argument or not, locally I get everything in an open neighborhood. Right. But if I have some other point in the orbit, say G of this base point, way far away, right? So here's the local thing, here's x0, and here's everything I get in here. This is good. And now we have another point in the orbit, G of x0. Well, this is G, this is a point, but it's contained, let's say this thing, this is the neighborhood W, it's contained in G of W. I just pushed over this thing in the orbit. Right? All of these points are in this orbit, so every pushover by G is in this orbit. So that shows that it's open. So every G orbit is open, and the manifold is connected. So G orbits are disjoint or the same. So if they have to be the same, otherwise it would be disconnected. So the result follows from the assumption. From the assumption. That and it's connected. I'd always assume that it's connected. Are you okay on this out? Every orbit is open because locally it's true. And if it's an orbit, if an open set is in the orbit here, then I push it over there, it's in the orbit there too. So it's open everywhere, so that's what it is. Okay. Now, Cartan knew about this stuff. I don't think Cartan proved everything. The following theorem is not due to Cartan, but Cartan certainly knew it and believed it. And probably if you pressed him on it, he could prove it. Theorem. There's a pair of names that we usually associate to this theorem, Myers steam rod theorem. These are also mathematicians from my lifetime, but these people proved this theorem, I think, before the Second War. This is a rather old theorem. The isometry group of a Riemannian manifold is a Lie group acting properly on M. It's a hammer. It's a hammer. It's a hammer. So, it's a hammer. You have an arbitrary Riemannian manifold, and you have the isometry group, and we just proved that it really appears somehow in symmetric spaces, the isometry group. It's a Lie group. It's not just some, do you understand? if you look at some completely crazy thing without the metric, the group of diffeomorphisms on something, or, you know, without any further structure, these things are horrible. So you look at physics, and you look, for example, at Hamiltonian flow. The flows on Hamiltonian flow is symplectic. They preserve the form. So these are symmetric. These are symplectic isomorphisms. Now, symplectic form is not a positive definite metric. They preserve. We were just talking about college. His brother is studying this stuff. They preserve the symplectic form. But the Hamiltonian flow, for example, in 2 dimensions, the symplectic form is dp dq. You physics people know that form. You look at all the flows that preserve that form. Yeah, that's a horrible infinite dimensional space. That's the problem. That's a horrible infinite dimensional space. In that sense, the isometry group, in the sense of symplectic geometry, is huge. Yes, for non-compact manifolds. So the space of Hamiltonian transformations on a vector space is huge. Therefore, it's very hard to find invariance of this. And that's one of the deep contributions of Gromov, of understanding really what are the invariants of this huge dimensional thing that's very complicated, even just acting on a vector space. Here, it's a finite dimension. When I say Lie group, it's a finite dimensional manifold, which is a group. Okay? Always, acting properly. So, remember what a proper action is? It means that the mapping gx to x cross x, which takes gx to g of x, is proper. That is a definition, so you have a definition in front of you. But it means much more. You've experienced this in my lectures. It implies that the isotropy groups, G's x0, these are the G's that preserve, these are isotropy groups, such that preserve the point, is compact. It implies that orbits, which are just the space of orbits, an orbit here is the whole thing, which you get in the group, is closed. And this is not quite equivalent, I guess, but it's very close. It also means that x modulo g is Hausdorff in the quotient topology. So you write down this wonderful condition of properness, and it really means these 3 things. And I'm never sure if that's equivalent, but it's close. Okay, and those are the 3 things you really want, right? The isotropy is compact, the orbits are closed, and the quotient is Hausdorff. Okay? So the action is proper, it's a Lie group, it couldn't be better. Okay? So we have, in this case, a wonderful situation that if M is symmetric, globally symmetric, then the isomorphism group M, which we call G, is a Lie group acting transitively. And with isotropy groups, say at the point of consideration, G isotropy at x0, the point, everything that leaves a point fixed, set of G that fixes x0, we write, dedicated to our German friends, K is compact. It's the same word in German as in English, but it's spelled with K. Okay. So where are we in discussion? On the blackboard up there. I define globally symmetric. It means just what you think. Time reversal is everywhere. All right, that's good. Now you compose these time reversals, and time reversal is really an isometry, and you compose them, and you get a given 2 points. If you get the right flipping around and flip around and flip around, you can prove that you can map that point to that point. You prove that the group of isometries acts transitively. You can map any point to any other point. If I'm discussing this as a group of diffeomorphisms, this is not a useful theorem. But this thing is a Lie group. That means it's a finite dimensional manifold. Everything's wonderful. And using this theorem here, everything is perfect. Particularly the isotrope is compact. Okay. So now I state Cartan's theorem. Well, maybe I've stated it. Wait a minute. Have I stated it?
Right here.
Where? Where is it?
The simply connected.
Oh, there it is. Curvature is invariant, given only if this is a symmetric space. And now look at the classification. Classification is 1, curvature is invariant. Okay? And now Cartan's theorem is if and only if MG is a symmetric space. Okay. 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 On. So when I was a child, too bad my mother cannot hear this story. I loved to look at birds. And I love to look at books with pictures of birds. And one of my favorite pictures of birds is a picture of what is called a turkey in English, what is called a turkey vulture. Do you know the word vulture, maybe, in English? It means birds that eat dead animals. They're very useful birds. And these turkey vultures, I used to love them. They sometimes would they come in 5 or 6 of them, they discuss this dead thing, and then they pick on it, and they discuss, and they pick some more, and they discuss, and I just loved it. And quite often they have their wings like this. I don't know if you see it, they have their wings like this, drying in the wind somehow. Like the big, enormous birds. And when I was young, when I was a child, I wanted so badly to see a turkey vulture, so every bird I saw was a turkey vulture. I would come home to tell my mother, I just saw a turkey vulture. Of course I did. It was very hard to see a turkey vulture. So every time you turn around, you want to see something. And so therefore you claim and hope that you saw something. And you claim and hope that everything has to do with a Lie group, because the last 50 papers I have written are involved with Lie groups. And so when I see Cartan's theorem, I say, it's like a turkey vulture, so wonderful. I go home and tell my mother, you see, I saw a turkey vulture. Everything is a turkey vulture. But of course, it's only class 1, right? And class 2 has a big class in it of acting transitively on the unit sphere. And second of all, this is a symmetric space if pi 1 is trivial, because I use simply connected here. otherwise, it's what we call locally symmetric. It means it's symmetric space modulo discrete group. Okay. But one heck of a lot of mathematics is in the discrete group. As you see in dimension 2, in the most interesting case of the hyperbolic geometry, this is sectional curvature -1, sectional curvature 0, sectional curvature +1, constant sectional curvature. The geometry here there's nothing to do. Here it's just tori and so on. There's nothing much to do. Here, everything is to do with the discrete group. Okay. So the problem is, even though I saw a wonderful turkey vulture, everything is here. My Lie group is here everywhere. I'm very happy. In fact, it's wonderful. This is symmetric space and so on. But there's a lot of work in the discrete group. And second of all, there's a lot going on here in special holonomy and a lot going on in this other case. So even though it's a wonderful classification theorem, it makes me very happy for somebody who uses symmetry in my daily life. It is not the end of the story. Okay. So this says, and Cartan knew this, that you should study actions of Lie groups. Because, I mean, all of this, everywhere you look here, there's some Lie group acting that you have to understand, and particularly in this case. Okay. So let me comment on the actions of Lie group. And then we will make our pause, and then I will finish the classification of symmetric space. Okay. So the highlight of the last day of the course is I explain some foundations of Lie groups, and then I will explain the classification of symmetric spaces. That means I will explain exactly everything in this class. Okay? And I will do the concrete examples in detail that you know the disk, the plane, and the sphere. Okay, and leave me that. So we have some background. So let's let G act on a manifold, be a Lie group action on a manifold. An action is a map. So this is the action. So it's a Lie group action. Okay. So we take an orbit of this thing. This is all the points that you can get starting from a base point. Orbit. You should draw a picture of everything in life. Here is X. Maybe it's discrete, maybe it's not, but let's pretend it's continuous. And here's this U. Now we take something in the isotropic group, G sub X. I'm going to have to try that. Oh, you stole it. You come here, the first thing you do is steal this. Okay. So if she takes something in here, and we have an associated map, G goes to the orbit G of x0. That is a map of G, given this thing. So an element here goes to the orbit. I have learned from my German colleagues who were very good at writing down trivialities. And I used to complain to them. My Otto Forster, maybe you know his books, is very nice analysis science and so on, a very nice book. He's a good friend of mine, Forster. And when he sits in the seminar, he's always screaming at me to write down some triviality that I get mad at. But in fact, he's right. If you write down it carefully with these trivialities, you don't make mistakes and you understand what you're doing. So I've written down a triviality. You have this map. It goes from the group to the orbit. Excuse-moi, I take G and I hit X with G and you see where you go. I mean, that's, okay, Otto, come on, you understand. He says, yes, I understand, but write it down. Yeah, this is a good guy, this is a very good guy, by the way. You have to get used to this guy, Otto Forster, because he's Bavarian. So, but it's a very nice guy. He's still giving lectures. If you have a chance to see the lectures of Forster, they are absolutely perfect. So you have a mapping from the group to the orbit, it's this thing. Yeah. And now what happens if I take an element H in the isotropy, right? And I see what GH does. I'm thinking of Forster now. Forster very slow. But at the end, Forster finishes things. Very slow. Okay, Alan, take a point in the isotropy, multiply on the right-hand side of G with H, and see where it goes. Write down, Alan, where it goes. It goes to GH. Yes. H is in the isotropy, doesn't do anything. It goes to this point. Yes. And then, of course, Forster allows me to say that, let me call this H to make it easier to write. He would say H for Huckleberry. So I say, I call this my group. He says, okay. And so I say, okay, that's the same thing as saying that this map above, okay, let's call this map the action map at alpha. So it says action map of alpha is H invariant. On the right. Right? Because if you do anything here on the right, nothing happens. That's the action map that nothing happens. Okay? Then Otto allows me to draw my favorite picture. He has this in his head, but he would take 5 minutes drawing it, and I just draw it. Is I have the group H going through the identity. Here's the identity, and here's the group H. And here is some other element. And here is an element G. And here then is everything you get GH. All right? That is the action of H on the right. Right? I put G and I just act on the right. Okay? That is a proper free action. You check it, it couldn't be better. Yeah? And a point G goes down, we go down here, a point G, well, this is the orbit. Well, I won't say this is the orbit, it's just the quotient right now. And the point that corresponds to the identity is just H, this is H. And down here is the point GH. This is the quotient. And now when I was taking algebra from a genius mathematician named Paul Cohen at Stanford, who was explaining to me everything very nicely, and I was a stupid student. You were much better. Yeah? And he was explaining all this stuff like this. And like Penkov explains this stuff like this, and here's a coset, right? You hear the word coset, right? These people call that a coset. Well, it's just the equivalence class of that orbit. Right? That's what it is. And this space down here, we therefore write as G modulo H, and we write it as G modulo H. It's G modulo the right action of H. Yeah? Right? And of course, you have a map. Now Forster would be a little bit mad, but he would write it so quickly and beautifully that he would explain this to you. You have a map from G, this is G, to the orbit. G of x0 to the orbit. Okay, you have that map. And this map x, a point G goes to the point G of x0. And you just check that this mapping here is an isomorphism. Right? You check it. This map is an isomorphism. You understand what I'm saying? I told you this mapping here was H invariant, right? By the right action of H. It's H invariant. Abik is absolutely not happy with this, I can see.
It just looks like one of those isomorphism theorems.
I don't know, it is one of the, at the level of linear algebra, this is exactly the so-called isomorphism theorem that it factors through G modulo kernel. This is nonlinear. This is a legal, but it's the same theorem. So I'm glad you mentioned that. It's the same theorem as one of the isomorphism theorems of elementary linear algebra, right? That's what you're thinking about. Or it doesn't matter if you have a normal subgroup of a group, it doesn't matter. But this group H is not normal. This is just the coset space, but it's okay. So I'm happy that Abik mentioned this theorem. In algebra, this is just the isomorphism theorem. Yeah. Okay, so that is an isomorphism. And then the good students here, since you're all good, you would ask me, what kind of isomorphism is it? Because this thing is not a group or anything, I mean, it's just this. And the answer to that is, locally, this is a trivial bundle. This is a bundle. Locally, it's locally trivial. This is a theorem of Sophus Lee that he worked very hard to prove. It's trivial to prove it nowadays. This gives you coordinates on the base. This gives you a differentiable structure on the base. This is a principal bundle with differentiable structure given by the local slices in the bundle. Okay? So the differentiable structure is here, and this then gives you an injective immersion onto the orbit. So it's Abik's remark. In algebra, this is just the isomorphism theorem of some sort. I mean, it's mod out by the kernel or something. Right? That's all you're doing here. But here you want it to be smooth everything. Right? And so you prove it has local smooth structure that factors like that. Okay. So the orbit has smooth structure is the image of a differential manifold, which is a manifold equipped with action of G, Gx on this. This is the action of G on this is, say, G of a point G0 H. This is the action. It's just G. It's just the left action. So if you mod out by the right action, the left action you still have again. So this is the action that you're getting on the orbit. So this transforms this action on the set of cosets to the left action on the orbit. So we say that this mapping is equivariant. Okay. Now, somebody coming? I'm about to make a pause now, but one last remark. If the action is proper action means that the orbits are equal to G mod K, where K is the isotropy, is compact. Well, I told you, proper action means a lot of things, but in particular, the isotropy groups are compact. So we have a result, proposition. When you see this from the point of view of Lie theory, and I'm sure when Cartan proved this, he was extremely happy. He went home and, I know he had a wife because he had a son. Well, maybe he didn't have a wife, but anyway, he had a son. So, but I think he had a wife. By the way, the Cartan family was very liberal. It was known to Adolf Hitler and his SS and so on that the Cartan family was living together someplace in Paris, for example. And mathematicians knew about Cartan, and some mathematicians were working against Adolf Hitler and some were working for Adolf Hitler. I can make you a list if you want. One of the very close members of the Cartan family was in Toulouse protesting against Nazi regime and things like such. The SS went to Toulouse and killed this member of Cartan's family. It may have been Henri Cartan's brother, it may be his son, I think. Can you imagine this? Kid. I would not, yes. Can you imagine this? In 1945, there was peace in Europe. In 1946, Henri Cartan was in Münster lecturing to German students about results in complex analysis in Riemannian geometry. Yes. Think of that. Think of these horrible things and think of the destruction of Germany. Think of Münster was flattened. He went there to help Heinrich Benke and the people who, of course, didn't do anything in the horrible times of World War II, even though some very close family member had been assassinated by the SS. This is really an example of what you should do. Yes, but nobody, very few people do it. Proposition mg with invariant curvature with M simply connected. This is no assumption, we could go to the base. If and only if M equals G mod K is a symmetric space. Right? I just put together a sequence of things that we proved, right? If it has constant curvature, then it's a symmetric space. The group of isometry acts transitively, is the Lie group. It acts transitively and properly. Therefore, it's a homogeneous space of the form G modulo H, coset space. But H is compact, so it's in this form. Okay. So, I will close the lecture right now. We'll make a pause there. Let me just tell you about seeing turkey vultures. Cartan was a person like I was when I was a child. Because before he proved all this theory, before all of this was introduced Cartan, he had studied symmetric spaces closely and had come very close to classifying all symmetric spaces before he had all of this theory. So when he looked at this Riemannian theory, it was like me looking at the turkey vultures, saying, I see, I came home to tell my mother I saw turkey vulture. Cartan saw symmetric space everywhere. Yes? But of course, Cartan was a genius. There were really symmetric spaces everywhere. And he proved this theory. And in the next lecture, I will explain the classification of the symmetric space. These things. So let's, how long do you want to pause? You want about 10 minutes? Is that okay? Whenever you get back here, 10 minutes. Okay?